Hi, welcome to this new lesson. We are now going to simplify the neuron by adding functions. Let me show you an example. So here we have the entire code that we use for our neuron. So we have already two functions, which are the sigmoid and sigmoid derivative. We have the input dataset, labels, weights, and here the neuron during the training. We are going to simplify all this code that is right here inside with just two functions. One is the feedforward and the second one is backpropagation. But before, we will see visually what is the feedforward and what is the backpropagation. Let's start. Right here we have the neuron. Now I'm going to take an image. We have the vertical image. And by the way, I'm not going to explain anything new in this video, but we're just going to review how to train a neuron. And in addition, I will use the proper terminology and explain what is the feedforward and what is the backpropagation. Let's start now with the first step, the feedforward. We start as usual with one image. We start with the vertical image. So let's say that we want to train the neuron to identify a vertical image. So we take the vertical image. We have to flatten the image. So I take this flattened image. Let's use it with the full size like this. Okay. So this is the same image in just one line. Now, this image has the values where the black pixel is 0 and the white pixel is 1. So our input will be 0, 1, 0, 0, then white pixel 1, black pixel 0, black 0, 1, 0. So this one is the input. Then after the input, we have the weights. Let's add weights. The weights are random numbers from 0 to 1. And we use 0.5 previously, so 0.5 for each of them, 0.5, 0.5, 0.5, and then last one, 0.5. So we multiply each value, so 0 per 0.5, 1 per 0.5, 0 per 0.5, and then after we have done the multiplication, we make the sum. So 0 per 0.5, 0, then here we have 0.5, 0, 0, 0.5, 0, 0, and then 0.5, so it's 0.5 plus 0.5 plus 0.5, and we have 1.5. So here we have the activation function. So we use here the sigmoid. Let's also write it here, sig of 1.5. And using the sigmoid, then we get an output. So let's call the green one the output. So sigmoid of 1.5. And it is equals to 0.81. This 0.81 is our output. If 0.81 is closer to 0, we can say that it is a vertical line. If it is closer to 1, we can say that it is a horizontal line. In this case, it is closer to 1, so it is saying it is horizontal, but we know that our image is vertical, so of course the prediction is not correct because the neuron hasn't been trained yet. And all these operations that we have seen multiply the input with the weights, then applying the activation function on the previous operation and then getting an output, it is called feed forward. Feed forward. So let me quickly summarize the feed forward operation. We start from the input, so our vertical image, let's say just input. Then from the input we go to the weights. Then from the weights we go to the activation function. And then from the activation function we get the output. In other words, the feed forward operation takes the input and using the weights and activation function gives us an output. Before going to explain the backpropagation, now we will go to our code and we will simplify the code to use input weights and activation function and output as feed forward function. Let's go. Okay, let's take a look at our code. We have two functions already, sigmoid and sigmoid derivative. We have the input and this stays the same, also dataset stays the same, labels stays the same, and weight stays the same. What we're going to change is inside the neuron, where we had the feed forward operation. Here is where the actual operation of the neuron happens. We have the image which we multiply with the weights, and then we have the activation function which gives us the output. For the moment we will just simplify this code with a function. So we can put this function wherever we want. It is a good practice to put it before the entire code, just below the other functions. So we can say def feed forward when we feed forward we need the image, so we need image and we need the weights. So we need image, weights. So image, we can just call it input. Input is our image. Weights, and that's pretty much what we need. So with image and weight we make the sum. First we multiply them, we make the sum. So we copy this one convolution just inside our function, and this is of course input, and then with the activation function we get the result and we return result. Okay, now we can use this function. We go here where we see convolution and result. Instead, we just want to get the result right away, so we say feed forward, and we the result is equals to feed forward, and we need to give the input. The input is the image, this one, image, and then the weights. And now let's print result. And let's run this one. And this is the result, which is the same as the previous video because we haven't changed anything about the neuron. We have just simplified it using a function. But this is not everything. We still want to simplify all the rest so that we can have just two lines. One is feedforward and the other is backpropagation. Just two lines to make all the functions of the neuron here inside. So let's now understand what is backpropagation. With the feedforward operation, so input, waits, activation function, we got an output. The output was equals to 0.81. And the image is supposed to be a vertical line, so 0.81, while it's supposed to be 0. Now let me prepare the neuron for the backpropagation. The backpropagation is an operation which starts with the output. So let me write here output. From the output, we're going to get the error. How do we get the error? Well, to get the error, we need to understand how wrong is our detection. To understand how wrong is our detection, we need the labels, and we have 0, which is the vertical line, and 1 is the horizontal line. So these are our two labels. If we train the neuron with the vertical image, we will use the operation 0.81 minus vertical, which is 0. So 0.81 minus 0. If we train the neuron with the horizontal image, we will say 0.81 minus 1. Of course, the neuron gets trained for all the images that we have. So first we will train it with the vertical and then with the horizontal. Now we're just going to see it with one image to make it more simple. So it will be 0.81 minus 0, so still 0.81. So let's write this red one, error. Then from the error, we can calculate the adjustment. To calculate the adjustment, as we have seen in the lesson, we're going to see the slope so that we can understand how much we have to adjust. To this number 0.81, we apply the sigmoid derivative and we got the result, which was 0.17. So let's say this is the adjustment. Then what we do? We multiply the adjustment for each single pixel. So we multiply 0.17 with 0, 0.17 with 1, 0.17 with 0. So let's do this. So we multiply this with the input. So let's write, this is the input. So 0.17 for 0 is 0, 0.17, then 0, 0, 0.17, then 0, 0, 0.17, and 0. Finally, we have to subtract from the weights that we already have these values. So we know that at the beginning all the weights are 0.5, so will be 0.5 minus 0 will be 0.5, 0.5 more minus 0.70, 0.33, 0.5, 0.5, 0.33, 0.5, 0.5, 0.33, and 0.5. All this operation from the output to the error adjustment input and then updating the weights, this operation is called backpropagation. So let me write it down here. We have backpropagation. So backpropagation starts from the output, then the error, then to the adjustment, to the input, to finally give us updated weights. So we can easily say that the backpropagation starts from the output and gives us updated weights. Now let's go back and let's see this right into the code. So after feed forward, this one, we have error, which takes the result and label. Then it calculates the adjustment, and then it gives us the weight updated. So let's now create the function. Just after feed forward, def backpropagation. What does backpropagation take? Let's now copy the second part of the neuron. So after the feed forward, we have the error, the adjustment, and that's what we need. And also temporary weights. Let's copy also this one. And we remove it from this part, and then we put this inside the function. So for the backpropagation, we need to give the result that we get after the feed forward, the label, so that we can compare how wrong was the detection by subtracting the error with the label. And then we need also the input, so the image. Here instead of image we say input, and finally we're going to return the weights update. Let's call it this way. Here it is going to be not minus or equal because we will do the operation later. Instead, let's call this weights update. I'm going to remove all the printing statements right here so that it will be just more clear without this. So now in these 3 lines it will be really simple to understand. Backpropagation, we have the error, so the result minus the label. The adjustment, we multiply the error with the sigmoid derivative of the result. And finally, we multiply the adjustment with the input to get the weights update, so that we can remove from the weights the value that we get right here. So here after the result, temporary weights will be minus or equals backpropagation backpropagation. So we need to give the result, the label, and finally the image as input. And now, to make sure that everything is correct, we are going to print temp weights and print temporary weights. And I see that after 100 iterations, the result is the same of the code that we used in the previous lesson. So that's enough for me to say that we did this correctly. Is this everything that we have to make to simplify the neuron? Well, that's not all. And now we're going to see one last operation in this lesson to simplify the neuron even further. But to explain this, I'm going first to print the output of the neuron, and then we will see what else we can make to improve it. Let's start from our dataset. We have dataset, we have all the images inside the dataset. So we have now just two images. First image, the vertical line, and second image, the horizontal line. And then we start with the round one. So we see for I in range and we print round one. Then when we start the round, we also loop through the dataset. So we don't do the operation in real time for them, but first we loop. So we start with the first image, and here we take the first image. I'm not printing the image, so it will be easier to understand if I print image and print image. And let's run this again. So I start with the first image, which is the vertical line, of course, 0, 1, 0, 0, 1, 0, 0, 1, 0. And we get the result for the first image, and we start updating the weights of the first image. We keep them temporary because we don't want to update the weights if we haven't finished with all the images. So we store them, the value in a temp weight, so that when we have all the updates for all the images, then we can sum them together. Otherwise, we don't do it that soon. And then we go with the second image. We have 0, 0, 0, 1, 1, 1, 0, 0, 0, which is the horizontal line. And we get the result for the horizontal line. And finally, after everything is done, we get the weights for all the images. Now, what if instead looping through the images, we will be able to do the operation in parallel at the same time? So instead of having image 1 and image 2, we will start with the data set. So this will be the input. And then from this, what if we could get an output like this? So we have image 1, the result, and then we have image 2, which in this case is the same value, but it is just a coincidence. So just this first image and it is second image. So the first loop, of course, is just a coincidence that they are equal. By doing this operation in parallel, this process will be much faster. And this is possible to make using the library NumPy. So we will see how to do this right now. And let's start changing the feedforward function. So if we go up on feedforward take the input, which in our case was just one image, and the weights. Now we change this input with the entire datasets with all the images. And this is really simple. instead of using some input per weights, which can only work with one image, we will use numpy, so np dot input and weights, and we give the data set result. So I will just start with feedforward. I'm going for the moment to comment everything that we don't need. Instead of image, which we don't have anymore as we're not looping through it, we give dataset, and let's print the result of the feedforward for two images together, so for the entire dataset, and we print result and then result, and I'm going to run this one. So you see, first image, the result for the first image, second image, and the result for the second image. And this wouldn't work if we just use the sum operation, and I'm going even to show this. So before it will be sum input multiplied with the weights, and let's run this one. So this will be the result, a wrong result. That's an operation that we don't have to do. I was just going to show you the difference of these operations. So now we can remove this. Same thing we have to do later for the backpropagation operation. So we have a result, and now we can say backpropagation of the result, labels. So now we're going to give all the labels. So labels is exactly this one, numpy array. So we have two images. The first one, vertical line, vertical is 0. Second one, horizontal line, 1. Labels, and then the input, which is the dataset. And so weights, we can say minus or equals the result of the backpropagation. And so we can remove everything else, even temporary weights. And let's now run this one. And we get an error. So there is something to fix on the code. The best way to understand what we need to fix is to see where we get the error. So we have line 53. Line 53 is where we call the function. But then inside the function, the first line where we see the error is the line 22 in this file. So we go on the function backpropagation, and here we have line 22 where we have the error. So we're trying to multiply the input with the adjustment. So let's print error line so we can see it. So we print the input, and then we print the adjustment. Let's see this. Here we have the input, and here we have also the input, and here the adjustment. Here it says value error shapes 2, 9 and 2 not align with the dimension. So we're trying to multiply an array which has a shape of 9 pixels with one that has a shape of 2. But our goal is to multiply this one with this one with this. So for the first image, we multiply this with the first value. For the second image, we multiply each number here with the second. the array, if they are this way, don't multiply this way. So this is a multiplication which works when we have the exact same arrays. Instead, if we want to make such multiplication, we have to use an operation which on NumPy is called transpose operation, and it is just adding .t to the input, and we will see how this .t changes the things. Let's run this. So in this way, that's what we wanted to achieve. Instead of having the images, so one image in one line and second image in rows, so first row and second row, instead we have them in columns. So here we have the first image 0, 1, 0, 0, 1, 0, 0, 1, 0. The first image is this column which we multiply with the first value, and then we have the second image 0, 0, 0, 1, 1, 1, 0, 0, 0, which we multiply with the second value. And so this is correct now. And we can remove everything inside the loop, like all the printing which are not necessary inside the loop, and we can go back to our 100 rounds and we can now try the neuron. So we run this, and after round 100, that's what we get. So the weights are the same that we had in the previous files, but just our neuron is much more simple. So keep in mind feedforward and backpropagation. And by using these parallel functions of NumPy, we don't see anything different really in the speed right now because we have almost no data, but with bigger data sets, this makes a huge difference. This is all for this lesson. See you in the next lesson.